Maybe. All right. So used to last time when I was here, no, I had one person here for 238, but for 237, the projector was off. Okay. The one that was here, Victor. Yeah.
V for Victor. I mean, isn't that the word for it in the phonetic alphabet?
Yeah, right.
Victor.
Yeah.
I couldn't remember that.
That's not what I want.
What's your vector, Victor?
Yeah. Why is it coming up that? Is it still trying to load?
No, it's going. It's starting.
But that's not what I usually get when I hit
What do you usually get?
the right-hand key. Okay.
Oh, you are recording.
I am recording. And we've been recording for 1 minute and 17 seconds, okay? And every time I hit this, oh, I know what it is. I didn't open PowerPoint first. Sorry. My bad. I forget I have to do that now. Okay, I know what it's going to ask for. And fortunately, I forgot to take it out. So let's see if we can get away with it. Maybe I need to leave my disk in from the last class, but then it's going to ask me. Now it'll give me fits next time, but we'll worry about that tomorrow. For tomorrow's another day. Okay. This is so much fun. Oh, I don't know if you noticed or not. Still have to do this and that and that. And that. Now we're on the same page, but it's reduced. They came in Thursday afternoon and resurfaced all the boards.
They didn't like chalk being over there, huh?
They didn't, yeah.
Some people prefer chalk.
I know, and I didn't request they do this. I didn't even request they did that, you know.
It's probably a good thing they did that.
Yeah, I think so too, because
It was
people,
kind of.
yeah, it was getting, I mean, they're more than 10 years old, those surfaces. But you know, those chalkboards go a lot longer. Chalk's a lot cheaper. If it wasn't for the dust, I would prefer chalk, you know.
I can't stand the texture.
Chalk, yeah, I know. I don't like wearing it all day. So, all right. Any questions on math before we get started?
Just what page are we?
We're in section 2.1 on page 36. We sort of skipped through some stuff that I didn't think. The modeling part, I just did a little modeling demonstration. No, just kidding. Now you're glad you missed Thursday, aren't you? Okay. All right, yes. Okay, except then it was dogs. It doesn't matter. Okay. Chapter 2 is where we're really beginning. First order differential equations. But we needed the chapter 1 just for the nomenclature pretty much. So we don't have to explain now what a first order differential equation is. You should know that by now. All right. And this first section's solution curves without a solution. That's a pretty interesting title, especially to start you out. seemed like they would go on and do the things that do have solutions, and then said, and if you don't, then do that later in this chapter. But they're doing it stuff just off the top.
Just because it's called a solution curve doesn't mean it has a solution.
Right. They start with this. They call it some fundamental questions. Oh, yeah, you got your books. I don't have to read all of it. Well, folks at home, I hope you have your books. If you don't, please get your books so you can follow along too. Let me hit the high points here. A derivative dy dx, pick up the right pen here, and let's get the right color. All right. The derivative dy dx, okay, pretty ugly writing here, of a differentiable function okay, if y is differentiable, y is equal to y of x. Okay, if that is differentiable, it gives a slope of the tangent lines at the points on the graph. Okay.
Back her up.
All right.
That's going to end it.
What is it doing here?
Click the X.
Huh?
Click the X.
The x. Okay.
I don't know what's going on with it.
It did this in the last class when I was actually using PowerPoint. I would be on a white screen, and I'd be talking like this, and suddenly the white screen disappeared, and all the writing I had on it disappeared. I'm going to say keep and see what happens. Okay. But I have to now go through all this stupid stuff again. Now, to you, it's the same, but I'm in presenter view. I've got to get out of presenter view and do this and that I think. Yeah. Okay. Now, if that is a differentiable function, then dy dx equal f of xy is now, if that's a differentiable function and its derivative is a function of x and y, which is legal to have, then this is a differential equation, first order differential equation, because the x could be squared, it doesn't matter there, but the y's are only first orders of y. Okay? Now, that's necessarily a differentiable function on some interval I of the definition. It must also be continuous in I, because we said if it is a differentiable function, if it is a differentiable function, it's a continuous function. You can't take the discontinuous function is almost by definition not differentiable. Okay, even some continuous functions aren't if you have that kind of points or cusp, but they certainly have to be continuous. Okay. Now, what the whole point here is, if you evaluate this function, pick a point, and this is what I wondered if I needed to do. I think I do. Let me see if I can, I don't know how to. I wanted to get back and pull up the graph thing. I forgot about that.
That's a different PowerPoint.
Huh?
That's a different PowerPoint.
I know. So how do I get to that?
Well, you can finish what you're doing here and then
In the show?
Yeah.
Okay. Yeah. Oh, that's right. Okay. I guess I'll discard that and come.
File.
What's that?
Go to file.
I do need to go to file.
Yeah. You
I thought I had it. We had it on the screen too, but
you can do it multiple ways.
yeah.
And then open. And then
Graph PowerPoint. There it is. Okay. All right.
From slide. You have to do all the function F10 stuff again. And
What's that?
function F10.
Yeah. Oh, that's right. And hide presenter view again, and function F10, and function F10, and function F10. Okay. Got it.
That's just, that was almost too big.
What's that?
There it is. It's just the right size.
It's what?
It's just the right size.
Yeah. Now it brings back. It looks like to me it's a little on the fuzzy side of it, but I don't think that's about as good as we can get, I think. All right. What you wind up with then, I wish I still had the other thing here. Let's go. And of course I have to go back and do this again too. All right. If this is your dy, dx is some f of xy, okay, then give me an x and a y point. That defines the slope at any point. So you can put a little slope line there. Go to a different point, you have a different slope line. Go to the previous point, you go all over the place and have slope lines. And then what you do is kind of connect the dots along the slopes. And you have a representation of that function. Okay? That's called when just all you have are the derivatives, and at every point you have a little arrow there. They call that a direction field.
Yeah, I remember doing that.
Oh, you do? Okay. And by the way, that is called, the alpha of xy is called a slope function or a rate function, meaning the same thing. A rate is a derivative. Okay. Another piece of nomenclature here, we will divide a line segment at every point that we can calculate that. Any little line segment we put there, we call it a lineal element. It's the element at the right value, at the right slope, but the rest of it isn't quite precise. It's not necessarily a straight line. Okay? And then if we plotted all those in there, you would have what they call a direction field or a slope field. Okay? And I wish I had a slide of this. I am not about to draw one. But on page 37, if those are at every point that you had there, you put in the little lineal element that had the right slope at that point. Then they had no basis for starting the blue line where they did. In fact, it looks pretty bad. They went between those two blue points there, but then they went almost on top of the next line to the next one, and then the next one. They came a little bit better on the way out. Coming in, looks like they did the red does quite well. The first one, they started on a slope line there, went to the next slope line, then went to the next one, missed the next one a little bit, and then came down to the next one. So the green one, they started out between them again. They almost hit the next one really close, got off a little bit, and then it just didn't look like they quite got, but I guess they started off in between, so they stayed in between. I don't know. But anyway, that's how you can come up with approximate curves if all you have is your direction field. So example 1, the direction field for the differential equation. So we'll do it here. Dy dx is equal to 0.2 xy. Okay? Now, let's us draw in at least a few of these. And since they seem to like to do these in light blue, let's go to our ink color of light blue. Right there. And then we'll try to draw in that. So, at 0, 0, what you got? 0. So 0 slope there. At 1, 0, 0. At 2, 0, 0. In fact, anytime any one of these is 0, you have a 0 slope. Okay? But not just the x is being, y is being 0, x is being 0 also. So all these ones here are horizontal lines, 0 slope. So those are fairly easy, not much calculation there. Okay? So let's start maybe at 1, 1. That would be 0.2. So that's a very, very gradual slope, not much of a change. Let's do 2, 1. That would be 0.4. That's getting close to 0.5. Okay. 3, 1 would be 1.2, right? So that's just beyond 45. 4, 1, is that right? Yeah, 4, 1 would be, yeah, I'm sorry, 0.6. Yeah. That's, don't know why, yeah. Let's go back. Let's erase that one. I did a little too much there. Okay. Okay, that was a 0.6 here. Less than 1. A little bit more than the one before. Then 0.8 is getting closer to 1. And then 5, 1 would be 1 exactly. Slope of 1. And then the next would be a little bit greater than 1 and a little bit greater yet than 1. Okay, I probably have too much going up there. Then let's do 1, 2. That would be, so you see you can draw as many of these in as you want to and continue. Let's go on the negative side, and you've got these going downward here slightly, a little bit more, a little bit more, a little bit more, -1, a little bit more than -1, a little bit more, and so on. In this quadrant, they're also going downward a little bit more. Whoops, I went too much. This one's supposed to be a little bit more, a little bit more, a little bit more. One of these is, yeah. Okay. But anyway, you get the point. Fill in all those little things, and then you can start really anywhere you want to and kind of follow the arrow and see if you can get the curves to fit. They draw some of those curves in the next slide, in the B part of that slide, and they continued this in blue for I'm just going to estimate this here. something like that. But if you came in here, you would be, like this. They get steeper and steeper. What's that? Well, not quite. I don't think that first one would qualify quite as a parabola, or would it? Yeah, I guess it would be. It would just be
gradual decline
yeah.
at one point.
Yeah. But these would be the, they suddenly changed. Oh, no. I'm sorry, the B part is a completely different problem. Sorry about that. Oh, no, it is. That would be. But you see what the function is when they just threw this in. By the way, here's the one that fits that, okay? That differential equation would be y is equal to CE to the 0.1 x squared, okay? I wish they would go on and show you how to get there rather than say, oh, here's what it is. Verify this. It is what it is. But this would be a function that would do it. It's not a parabola. It's an exponential of a square, okay, which they begin looking like a parabola, but they're not quite. This one, C equals 0, I should have done, this is its curve, okay? C is equal to 0. I should have done while I still had this. These are C's greater than 0, and then the C's less than 0 would just be mirror images of, the ones above, Yeah, something like that. I don't have them quite being good at mirror images, but this would be C's less than 0. Okay. Now, again, if we had drawn in all the little arrows and drawn them correctly, then you would see how these curves kind of line up there, okay? And
it's kind of hard after a while to keep them at just the
absolutely. I mean, to draw them freehand, I can't do it, okay? What I wish we had done, in fact, I'm real tempted to go on and do it, show you how they got their function. Get back to this, because it just seems like such a pain in the neck to mess around with it. Sorry. I'll show you how they got that. Okay. This may not be black. I thought it was, but it may be. Yeah, really deep purple. That was a singing group too, wasn't it? Never mind. Okay.
singing group.
You never heard it?
No, I've heard of Deep Purple.
Deep Purple, yes, okay. Okay. So, here's how they get it. I hope this isn't jumping too far ahead. And this is where a pure mathematician would probably cringe a bit on it. No, not really. Write this in differential form. dy is equal to 0.2xy dx, right? That's a legal move, right?
As long as you don't tell them what you did get over there.
It's writing it in differential form. Okay, you don't multiply by dx. Okay, you're writing it in differential form. Now you can do this, divide both sides by y, right? Now what you call that is separation of variables. We're going to get that in a later section here. And then what we do is integrate both sides. I don't have a lot of room. So the integral of dy over y is equal to the integral of 0.2x dx.
When you pull that point 2 out.
What's that?
You pull that point 2 out.
Yeah, pull the point 2 out. What is the integral of dy over y? Yeah. No. If you take the derivative of y, you get 1. Not 1 over y. Log y, exactly. Natural log of y. And take the integral of the other side. What do you get? Pull the point 2 out. And what's the integral of x dx? No. Antiderivative of x. It's x to the 1. Yes. X squared over 2. All right. And the 2 will go into point 2, 0.1 times. Okay? So, if you don't want log y, you want just y, what do you do? Yeah, raise the e to e, and that would be y is equal to e to the 0.1 x squared. And you could say a plus c, which would be fine, or you could say a plus e to the c. That's also a constant, isn't it? And if you had that, that's the same as c e to the 0.1 x squared. Yuck! It did it again. I think I know what's happening.
Hit the back arrow.
Back arrow
Like, yeah.
on the bottom.
And hit it one more time.
Ha! Thank you. It was messing up in my last class too. What is happening is, if I write too close to the edge,
It will proceed to the next slide or to the end.
well, I don't know what it does. I guess it goes to the end. Yeah, it ends. That's what it was trying to do. Okay, so I'll need to remember that. This is how they got their formula, their equation. Y is equal to, or alpha of x is equal to that. Why they do this and say, here, this is the function that works. Why didn't they tell you how they did it? Well, they said, we saw in section 1.1. All right. Let's do example 2. Okay, it says use a direction field to sketch the approximate solution. So what I think I'm going to do here is erase all the ink. Yes, that worked. Okay. Use the direction field to sketch the approximate solution for the initial value problem dy dx is equal to sine y. Now, this is a first order differential equation, but what is it not? A linear first order, because the function of y. If that had been sine of x, no sweat, but it's sine y. Okay. On this one we have a initial value, y of 0 is equal to negative 3/2. Okay? So we want to find that. Okay? What's that again? No, that's what y is. Y is equal to 0. Y prime would give you the slope there. Okay, so here's cheating a little bit. Let's go right to that. We know that y of 0 is equal to negative 3/2. So that would be right there. You know that point is on the curve, right? Okay. Now, we take this and we say, what is sine when y is equal to negative 3 halves, what is sine of negative 3 halves? Oh, that's right. It's not 3 halves pi.
Yeah,
I was going to say.
like,
Yeah. Okay. Pull out your calculator and figure out what it is. Be sure you're in what mode? Radian mode. Okay.
You're lucky. I got the old calculator.
Ah, okay. That'll work. Okay.
Yeah. It's the faster one. I don't have to wait for it to turn on.
Yeah.
Alright, so sine of
Negative 3 halves.
2, and I'm in degree mode, so let me fix that.
Maybe.
Negative 0.997.
So that's almost a negative 1.
Almost.
Okay, I'm going to draw it. That's almost a negative 1. Okay? So we know it's going downhill from there. Okay? Boy. Let's just do a few others. When y is equal to 0, we know that all those are horizontal curves, horizontal slopes, right? Okay. When y is equal to 1, what are our curves there? You'll have to plug that in. Sine of 1. Be sure you're in radian mode.
That's 0.84.
0.84? Okay, I thought you said 184. I thought, really? Okay. 0.84. So when y is 1, 0.84, that's just short of, and these are all the same for all those y's, right? I'm not even sure we need to be up there, but I want to do that one to give you one that you're a little, maybe. And I'm going to guess that sine of negative 1 would be negative 0.184, right? Okay. Okay, all these are the same here for the y's. Okay. How about negative 2's? What would they be? Sine of negative 2.
Negative 0.9.
Okay,
Nearly 1.
okay, but the negative 1.5 was even more negative than 0.9, wasn't it?
Yep.
Okay, so this is now sloping up a little bit. The maximum slope it can get is negative, or minimum slope is negative 1. Okay, so this is coming up a little bit. How about negative 3? Give me what that one would be.
Negative 0.1.
Negative 0.1. So that's a very shallow slope.
Who knew the slope could be so shallow?
What's that?
Who knew they could be so shallow?
I can't hear.
Who knew they could be so shallow?
Yeah, right. And then negative 4. I'm guessing it's slightly positive.
Yeah. 0.75.
Ooh, nicely positive. These are not very even. Okay. So what I'm guessing is happening here is this slope is going down here, leveling off, and then it looks like when it gets down here, it alternates. It almost, that doesn't make any sense. Okay.
And wouldn't it be going like this?
Huh?
Wouldn't it be going like this along the y-axis?
Yeah, we haven't done anything there, but
It's just a sign of one.
yeah. But you see, your dy dx is fairly negative here, less negative here. Somewhere down here it goes positive, and then it goes negative and then positive and negative and positive. It seems like it has to do that, which is kind of bizarre. Okay. Now I may be doing something wrong on it. No, it doesn't. It actually flattens out. Okay. That's what it does. It just comes down, and somewhere in between there, yeah, that makes sense. Somewhere in between there, between -3 and -4, it has to be 0. And when it reaches that 0, it stays 0. Or is approaching the 0 and approaching it and approaching it. So that's what's happening. And then somewhere up here, it's doing the same thing. Here, it was, oh, right there, it's 0. So, right, yeah, it's the x-axis is doing. So, that's your curve right there. Okay. So it doesn't get oscillating, it just does the other. Okay. Now, oh, and I know exactly, yeah, it's at pi. Yeah, 3.14 is the -1, 2, 3. Negative 3.14 is that place where.
Okay, so it's kind of reminds me of the
Inverse sine function.
or actually it reminds me of inverse tangent. Or well, no,
No,
regular
yeah,
tangent.
yeah.
But it just flipped on its side.
Right. Yeah, that's exactly what it's going to look like. Okay. Yeah. Now, again, we're into mostly nomenclature here. What do we mean by, and by the way, sketching the direction field by hand is straightforward but very time-consuming. What a statement. Before calculators, PCs, and software, the method of isoclines was used to facilitate sketching direction. And this is basically what it would say. The slope, the inclination, isocline.
It would plot all the little.
Yeah.
And
And
you
just,
had to figure out where the line.
exactly. All right. Now, let's now look at what they call autonomous. I think that's how you pronounce it. First order differential equations. We hadn't hit this word before. In section 1.1, we divided a class of ordinary differential equations into 2 types. Well, of course, let's start. Ordinary and partial. We're not doing partial, it's ordinary. Then ordinary was in 2 types, linear or nonlinear. Now we consider briefly another classification of ordinary differential equation. That is a particular importance in qualitative investigation of differential equations. Ordinary differential equation in which the independent variable does not appear explicitly is said to be autonomous. The independent variable does not appear to explicitly. Okay? Yeah, autonomous. I guess you're right. Yeah, autonomous. I was thinking autonomic nervous system. So, yeah, autonomous. You're right. And if the symbol X denotes the independent variable, then the autonomous first order differential equation can be written as y. When you take include. Oh boy. Let's see.
You have a blank slide.
I think we need to go to a blank slide here.
You can hit the right arrow.
Okay, right arrow.
Or just click.
Yeah, let's click off of that. Okay. Okay. That gets us in. Thank you. Okay. So let's get out of the blue. Okay. F of y prime is equal to 0. Okay. If it's a first order differential equation, the other way of doing that is dy dx is equal to, which is your y prime, is equal to some f of y alone. Okay. So in other words, if you get this to this side, then f of y and y prime is going to be equal to right. So there is no x dependence. Okay. We shall assume throughout that the function, and by the way, that was an autonomous function that we just had, because the dy dx was equal to sine y. No x dependence at all. We saw that. Okay. We shall assume that the function here, the second equation here, and its derivative f prime are continuous of y on some interval. Then the first order equations, here are some. Dy dx is equal to 1 plus y squared. Now, what is that not? Okay. It is a first order differential equation, but it's not a linear differential equation. Okay. Because you're y. If it would have been x squared, yeah, it still would have been. But
if it was like d2y, that would have been.
Then the second order, yeah, d2y, yeah. Or y double prime, yeah. Yes, exactly. That's why I go back and ask these questions. Here's another one. Dy dx is equal to 0.2 xy. Is that autonomous differential equation? No, it's not a function of y alone. It has an x in it. So this is autonomous. That one's not.
But this one is linear.
Okay. Actually, yeah, they're both first order because the derivatives are first order. I have to go back and check the definition fully. I know if x is multiplied by y, somehow to me that feels nonlinear. I've got to check the definition and see. I know if y is not raised to any power, but you do have a product in here, and I'm not sure the products keep the linearity or not. I'd have to go back and check on that. What's that?
In example 1, that's the
yeah, that was the same as we had in example 1. That was exactly it. But did they say there it was linear? I don't think they said. All they said was differential equation. And they're just doing first order. They're not differentiating linear and nonlinear here. Okay. Now, many differential equations encountered in applications and equations that are models of physical laws do not change over time are autonomous, because most of the time is your independent variable. You can't do much with it, so that's your independent. If they don't depend on time, then they're autonomous. Okay? Here are a few examples that you'll run into. dA dt is equal to KT, KA. If that was KT, that wouldn't be autonomous. This one is autonomous. Okay? Now this would be something like your change of your concentration is a function of what the concentration is. So if you have a huge concentration, then it's going to change rapidly. This will be a big number. If you have a very small concentration, it's going to change much more slowly. And that kind of makes sense. That's a good physical thing. If you think of crossing a semi-permeable membrane, right? If you have a huge concentration here, basically no concentration there, it's going to go really quick. Yeah. But if they're almost the same, it's going to be a very slope. So that is an example of that. Okay. When I see the A there, I think amounts, and that's why I thought concentration. dx dt is equal to kx n plus 1 minus x. Yeah, okay, right. I was looking at that and saying, hey, yeah, your x is your independent, is your dependent variable. Yeah, so that can be there. The time just isn't.
And then have nothing to do with
Exactly, they're just numbers. Okay, so the key is your time isn't in that anywhere. Now, for the life of me, I cannot think of what that's dealing with.
something made up.
It probably does have some, but I'm just not familiar with that one. How about this one? The symbol almost gives it away. dt, and when you see that physically, what do you think?
In relation to physics?
Yeah.
I can't remember what it was.
Temperature.
That's
Whereas little t is time. And this is, I think, pretty close to Newton's law of thermal equilibrium or something like that. I probably have the name wrong. But you see, the time is not important there. It's the how much your temperature gradient is. The change of temperature is dependent on how far your temperature is from ambient. That's what I think of it. I'm used to seeing the T0 there. TM.
might be zero.
Uh,
I said it might be zero.
Yeah. So, and that would be, I mean, that makes a lot of sense too. If you're heating, say, a light bulb right here, how is the temperature changing here? Okay, it probably not a huge amount of change. Let's see, is that right? Right here, you would have a great change of temperature. The rate would be really great. Here, it would be much less. Yeah, because it's falling off. So your rate of temperature change is very great, depending on the change in your difference in ambient temperature. Okay. Here's another that I would think of amounts, dA dt.
6 minus 1
Okay. I don't know. That's some very specialized type thing. This would then be going in the opposite direction, kind of. If A was very large, then this would be.
You could say it has something to do with cooking.
Could be. I don't know. It could be a leaky drum. Okay. Whereas the amount of that probably wouldn't quite be right. So again, what do you think?
Where 6 is like the amount it has started to start, and then
Yeah. The problem with that is I would think. Yeah, but it would be something that something is leaking out of. I think that's what this is relating to. That would be my guess. I don't know. It's sort of a specialized type problem. Now, so those are all examples of autonomous first-order differential equations. Whether they're linear or nonlinear, we're not even thinking of that. Okay, just first-order autonomous differential equations. Okay, critical points. The zeros of the function in 2, that would be this thing right here. The zeros of that function f, okay, are of special importance. We say that a real number C is a critical point of an autonomous differential equation if it is a zero of f. That is, if f of C is equal to 0. Okay? Okay. Follow from that. If this is true, then we say C is a critical point. And we did that before, you know. What's that? Oh, it went again. Sorry. I didn't see that go that time. Okay. A critical point is also sometimes called an equilibrium point. Okay. Or a, what you say, stationary point. Now, what you say? Okay.
That's one of the instances.
All right. Yeah, that would be, because f is your derivative, that would be, yeah, where the first derivative is 0. Right, exactly. Then these would be critical points. Right. Now, sorry, losing my voice here. If C is a critical point of the first thing, then y is equal to C, y is x equals C is a constant solution of the autonomous differential equation. Okay. All right, what I think I'm going to do is erase all the ink and go back and write in some of it. We're basing everything on this. Y, dy dx is equal to some function of y, not of x, of y. Okay. And the critical point would be anytime that f of C is equal to 0, C is a critical point. Okay? Now, going the other way, if C, say C and write F, okay, it's making a lot of sense. Okay. If C is a critical point, well, this almost sounds like Cal 1, of this equation, 2, then y of x is equal to C, okay? If C is a critical point, then when that y is equal to C, okay, then you're doing an alpha C, and alpha C is going to be 0, okay? Almost feels like you're running in a circle there. The y of x equals C is a constant solution of the autonomous. Is a constant solution of the autonomous differential equation.
What are they saying? When y of x equals C.
Okay. If you think of this, when y of x equals C, for any value of x, y is always just constant C. Okay? Okay, well then, and if y is equal to C, and C is a critical point, because that's what we're given, then that would then be dy dx is equal to 0, because derivative of your...
So it's just a flat line at a point.
Yeah, okay, exactly. And
I'm
then,
just trying to picture this graphically.
right, and yeah, that's exactly what you're supposed to be doing, so that's perfect. It's a constant solution of the autonomous differential equation. Constant solution is also called equilibrium solution. The equilibria are the only constant solutions in that equation. Okay? Now, if you think back on our curve y is equal to sine x, it went like that. When it gets flat here, those are your constant solutions. Not that it ever quite gets there, but that one.
Could it?
Well, I mean, when it's equal to.
But there's no like asymptotes there, for sure.
Right.
There might be, there might not be. It's not for certain. Okay.
Yeah. So. All right.
Gathering and understanding.
All right. Let's see. Let's start with, and we might need the graph. No, this isn't what I want to do. Okay, let's take this one and erase all ink. I can do it here. Okay, I wasn't sure it would after we had already passed it. Here's example 3. The differential equation dp dt is equal to P of A minus BP. Gulf oil spill. Okay. Where A and B are positive constants. Let's just write them here. A, B greater than 0. Okay. Has the normal form dp dt is some function of p, obviously, okay, which is that with t, which is equation 2, with t and p playing the parts of x and y. Yeah, okay, got it. Why don't they say t is your independent variable and p is your dependent variable, okay? Hence autonomous. We know it's autonomous. From f of p so we know then that this is equal to that. So f of p is equal to p times a minus bp. Okay? And when we want that to be 0, when that's equal to 0, then either p is equal to 0 or p is equal to a minus bp equals 0, then a is equal to bp and p is equal to a over b. Okay. Either of those two places, you're going to have constant flat lines there. So when p is equal to 0, you're going to have obviously your slope of that function is going to be 0, and when p is equal to a over b, whatever that is, then you're going to have a flat line. So if the p's in between there are your varying p's. Okay? Those are your critical points. These are the C. I hate getting so many different variables in there, but those are your critical points. We'll just call them C's. Okay. So the equilibrium solutions are P of T is equal to 0 and P of T is equal to A over B. By putting the critical points on a vertical line, that's your p-axis, okay? We divide the line into three intervals, okay? So let's let this be our p-axis, and this is our time axis, okay? So when t is equal to 0, t is equal to a over b. Let's just pick a point somewhere up there for that to be, okay? Like right there. This will be a over b. P is equal to a over b. All right. Now that splits the y-axis into three parts. The part that's up here, the part's here, and the part down here. Okay? Now, the arrows on the line indicate the algebraic sign of this. Okay? Now, when P is equal to A over B, this obviously is 0. Okay. When you're greater than A over B, okay, then let's just say 2A over B. Why not? So make it A minus B times 2A over B. It's obviously greater than A over B. A and B are both positive. Okay. So that's going to be a negative. Your P is decreasing there. When A is in between, when P is in between 0 and A over B, let's just call that A minus B over half of AB. A and B are both positive, so this has got to be in between those. Then what you have is A minus A over 2. That's positive, okay, plus, okay. And what about down there when P is less than 0, okay? When P is less than 0, let's just pick a number less than 0. Why not negative 1? Let's just try it. We'll have a negative 1 times A plus B, right? Okay. A plus B are both positive, multiplied by negative. This is negative down here. So that's how they got their arrows in the book there. Your function is decreasing anytime P is less than A, greater than A over B, increasing in between 0 and A over B, decreasing again anytime it's less than 0. All right. And it's 0 at the function is equilibrium at 0 or A over B. Now, let's see. These are values for P. Okay. So, okay. Trying to figure out what they're saying here.
Just what they're saying is how it acts around the critical points, I guess, and how to find that.
Okay. 2 point. What they call this here, just the more nomenclature here, that's just called a one-dimensional phase portrait, or a phase portrait of the differential equation. The vertical line is called the phase line. Okay. I'm trying to picture what the function must be.
So the arrows down and the arrows up, that indicates the slope?
No, that doesn't indicate slope. That indicates what? The value for P. Okay?
So it's negative up there, positive in the middle, and then negative.
Yeah. And I'm trying to picture how that's going to look. If P is negative, say if it's down here, then It's an increasing function. No, I'm sorry. When P is negative, well,
So and P is the y-axis, so it's
yeah.
it would be negative for that. It's the same one as negative for T.
Say that again.
So like down here, it's going to be over here somewhere.
Right.
And then up here, it's going to be on this side.
Yeah.
And then up here, it's going to be on this side again.
Well, P is the vertical axis, so it's going to be
down here, up here.
yeah. Yeah. That it appears to me when.
See, I thought it was in relation with T.
What's that?
I thought it was in relation with T.
With T, right?
So it'd be like something like that.
Okay. Now, yeah, you may be right there. Except, it really doesn't matter when P is positive. No. When P is greater than A over B, which is a positive number. Okay, you're right. It's a positive number. I guess that has to be, it means it's decreasing. Yeah, that means it's decreasing. Its slope is decreasing. So if it's up here, it's decreasing. It's 0 here, and it's increasing anywhere in here, and decreasing again here. I just can't quite
Picture that.
visualize that because T is not in the picture yet. Yeah. So let's just carry on and see. Here they have, and now they get away from T, X's, P's, and T's. I think that was just to give you the phase portrait, and that's all the reason they did. Now they're going to talk about something else, is solution curves, okay? And different topic, okay? Without solving an autonomous differential equation, we can usually say a great deal about its solution curve, since the function f in 2 is independent of the variable x. Going back to not this one, this would be t, independent of t. We may consider f to be defined for any value of x, okay? Also, since f and its derivative are continuous functions of y on some interval of the y-axis, the fundamental result of theorem 2, goodness gracious, where is that one? 1.2.1. Where was that? It had to be in the first section. Wait, yeah, chapter 1. 1.2, in fact, is what? Still too far up. Still 1.3. Newton's law of cooling, that was the one I was trying to think of. I'd said thermal equilibrium, but Newton's law of cooling, I just happened to see it. Okay, here we go. 1.2. Yeah, there it is, there. Existence of a unique solution. Okay, that's the one we did before, okay? If we have a situation, rectangular, that's what that was. Okay. The fundamental results of that hold in some horizontal strip R in the plane corresponding to that interval I, so that through any point x0 in R, x0, y0 in R, passes only one solution curve. Okay? I think we got to go to okay, let's just get all the ink off of this slide. Okay. Here's basically what they're saying here. If you have some interval, and they're doing this in light blue, so I guess I'll do that too. Okay. And they chose them both to be positive. They don't need to. Okay. If your y's are between in this interval, okay, and you have a point anywhere there, there can only be one solution curve through that point. Okay? That's what they're saying here. So that solution curve has to go through there. They drew it like this. I thought they were doing this on the previous example. It had nothing to do with the previous example. Okay. That for that one point. You can't have multiple curves going through that same point. Okay, because your solution curves basically are iso something and they never cross. So therefore, pick a point and there's only going to be one curve through that.
The point right next to it might be a very similar curve or a very different curve.
Right, exactly. It depends on what you mean right next to it. If you meant right next to it above or below, yeah, they're going to be different curves. If you meant right or left, yeah, they're going to be different curves. But if it right next to it meant here or here, oh, they're on the same curve. Okay, so vertically next to it or horizontal next to it, different curves, but you could have 2 points near one another on the same curve, but they would have different, either a different x or a different y. Certainly both, I think. Okay.
I think we're out of time.
And we're out of time. Let's see where we'll start next time. Let's start next time. Well, let's see. We still got to talk about boundedness. So we'll start basically, I think we can probably safely do the top of page 40. Okay. And I will end this one.